bounds of an integral. This is sort of going back to our first ideas of sums of a rectangle. That you had upper sums and lower sums. Okay? In between A and B, you are going to have a smallest value, and you're going to have a biggest value if the function is smooth and continuous. Do you remember which theorem that was? Where if between A and B, your function is smooth and continuous, you will have at least one point in between A and B where you have a minimum, and at least one point between A and B where you have a maximum. Which theorem was that? That was our extreme value. So, using our extreme value theorem, you could find your minimum, which we have as little m, and you can find your maximum, which we could call big M. And if you use little m, it would be a nice rectangle where you just do length times width. If you use big M, it would be a bigger rectangle where you just do length times width. And the actual area under the curve has to be between those two. That makes sense, right? And that's how we got to our infinite sums and our actual areas, because we were able to bound our integral that the area is in between there somewhere. So this means just like we have a mean value theorem, we have a mean value theorem for integrals. When is the quiz due? Quiz number 2. You've got your optional major assignment due on Friday. So we'll make the quiz number 2 due on Monday. So the mean value theorem says that if a function is continuous over the interval from A to B, and first of all, for the bounds, you know that the area is between little m and big M as far as the height of the rectangle. There has to be a height somewhere and a point somewhere where you have the average, and then that area of that rectangle happens to be perfectly the area under the curve. That has to happen because somewhere we think of the bounds. As I go from M to big M, M is too small, big M is too big, and if I go continuously through all the values in between, somewhere I have to hit the right number. So that's the mean value theorem for integrals. And then we get to this idea that we can also find the average value of a function if it's continuous from A to B by taking the area under the curve and dividing by the length, which is connected to this previous idea, right? This point C would be the average of the function because this area is f of c times b minus a. So if I want to find the average of the function, I would just have to divide by this b minus a, and I would find this f of c value. And that's all that's done here to go to the average value of the function. Which is kind of, I don't know, it's kind of cool. Because, you know, you have to find your average for your marks. Some of you are very marks driven and like always trying to calculate what's my average going to be if I get this, if I get that, right? And now you imagine there was somebody who just kept putting in, all they did is kept putting in marks. And your actual grade was like a graph of all these marks that get put in over time. And you're like, what is my average? Right? Like if I said, your marks from the beginning of the semester to the end of the semester followed the x squared graph from 8 to 10, right? At the beginning, you were getting 64. 8 squared is 64. By the end of the semester, you were getting 100. 10 squared is 100. If the beginning of the semester started at 8 and the end of the semester started at 10, and all of your marks were an infinite amount of marks from 64 to 100, but they followed the x squared curve, not straight line. Straight line would be easy. What's the average between 64 and 100? You'd be like, oh, that's my grade. But the x squared graph isn't quite straight. So then what's my average in this class? If my marks followed that. And we use integrals to be able to find it. So we're going to find the average value of f of x, right? If you plug in 0, you would get 0. If you plug in 3, 4 times 27, 108 plus 6, 114. So it goes from 0 to 114. But the question is, what is the average on this? Oh, this is a good one. Maybe these are your grades. Start off the year really bad. Month 0, you got 0 on your first assignment. You're like, I don't need to do this. This class is going to be easy. And you realized that wasn't so good, so you started doing a few more assignments. Your marks got really good. Teacher gave some bonus marks at the end of the last assignment. You got 114%. And you're like, oh, but what is my average in this class if I decided that I was going to learn by doing 4x cubed every time? Plus 2x. Well, our average formula says we do 1 over b minus a. So b minus a is the difference here. It's just going to be 3. And then we do the integral from a to b of f of x. So we set that up with our numbers in there. I forgot a little. Right? When we write an integral, we always have to say what variable we're integrating with regards to. So that's what that dx is. So you're 1/3 from 0 to 3. How do we integrate? Well, we can integrate each of these easily by adding 1 to the exponent and dividing. We put that in square brackets and write from 0 to 3 on the outside, saying that we have to evaluate this definite integral from 0 to 3. Plug in 3, get that answer, plug in 0 and subtract. Ooh, not a good strategy for the course. I don't know if any of you set goals like this. Like, I'm going to try to make all my marks follow the 4x cubed plus 2x graph from now to the end of the semester, and strategically study just to start off with low marks and end with high ones. In this case, it wouldn't work out too well. You'd end up with an average of 30%. Just going to take out the calculator. And show you what the 4x cubed plus 2x graph looks like. We're going to set our window. We're going to just going to go from -1. I'll go from z. I'll go right from 0. right from 0 to 3. So how do we normally figure out an average of something? You add up all the values and divide by how many you have, right? What's the problem with a function? Is you have an infinite amount of values. And you have to figure out which one is at your average. And according to this, what we figured out is that this amount underneath balances out with that amount above. But even drawing it in there, your brain can try to average things out, but it's kind of hard. Because notice that at 30, we're still quite a bit lower than the 114. But we have less values, because looking on our scale here, from this point to the right, we have less high values and more lower values. So when you have that, that averages out to a lower class average, right? If I had a bunch of people do really poorly on a test and only a few people do really well, then the average tends to be lower as a result. So that's, but normally I would say, hey, maybe you could just eyeball this. But that would be hard on a function to figure out where that is. And what we're doing here, I guess, as far as an eyeball thing goes, what we're saying here is the area under the blue which is colored in the blue crayon, that should be the same as the area here under the red. So we have to kind of try to imagine, does this area here, does that seem like it would fill up that perfectly? Again, not the easiest to visualize, but that's the idea that's happening here. And that's how integrals are used to figure out the average value of a function. So here we have another one, x cubed minus 2x plus 4 on the interval from -1 to 2. I'd like you to try this one on your own and see if you get the average. All right. How did you do? So we use our average value. Again, the distance is 3. We're going from -1 to 2 of 3x cubed minus 2x plus 4. We do our integral, add 1 to the exponent, and divide for each of them. Evaluate it from -1 to 2, so we plug in 2, we plug in -1 and subtract them. And we get an average value of 4.25. Then part B, now we want to find all the places where that actually happens. And this is a calculator question, so what we can do is you can type in the original equation in your graph into y1 and just y2 equals 4.25. Very similar to what we did on the previous question to say the area. But when we look at the graph, it actually hits the graph 3 times. But again, we're only looking between -1 and 2. So the first intersection actually happens before -1, so we won't include that intersection. But there are 2 intersections that do hit within our values. One is at negative 0.126, and the other one is at 1.473. And the idea being at those places, the area under the rectangle would be exactly equal to the area under the curve. So there's homework listed